RGBUVQXYZ, Semantic Address Space Rendering for SSD-Resident Worlds. Proposal Target NVIDIA Research / Developer Technology Review. One sentence claim: RGBUVQXYZ is a semantic raymarching architecture where each rendered screen pixel resolves to the nearest visible occupied address in a disk resident XYZ /UVW /RGB matrix, then shades through compact semantic screen passes designed to approach data center style streaming behavior on consumer RTX hardware. Executive summary: modern renderers usually begin with assets, meshes, textures, materials, splats, acceleration structures, and shader binding tables. RGBUVQXYZ begins with address space. The world is stored as a sparse coordinate matrix on SSD where spatial address, traversal address, and base color identity are unified. R equals U equals X, G equals V equals Y, B equals W equals Z. The virtual camera is placed inside this coordinate volume. For every rendered screen pixel, a ray is marched through the resident pages of the hard disk backed XYZ /UVW /RGB matrix. Empty addresses are skipped. Addresses with render flags disabled are ignored by the color pass but may remain available for collision, occlusion, physics, XR comfort volumes, or secondary passes. The first address that is both occupied and renderable becomes the pixel's visible hit. The renderer writes that hit into a frame buffer like hit map, screen pixel, hit _XYZ, hit _of, depth, semantic _ID, state _flags, payload _ID. Later screen shader passes read this per pixel hit map and apply semantic shading, local Gaussian splat expansion, procedural reconstruction, temporal reprojection, foveated refinement, or fallback color. This keeps traversal deterministic and compact while moving expensive appearance work into coherent screen space layers. The architecture is intended to make RTX class hardware behave more like a memory-rich H100 for this specific problem, not by matching raw bandwidth, but by reducing what must be fetched, expanding detail only at visible hits, reusing previous frame hit addresses, and treating semantics as compressed executable shading keys. What is novel? RGBUVQXYZ combines 5 ideas that are usually separate. 1. Position-derived color. Coordinate identity can directly produce base color. 2. 2-bit plane traversal, 1 plane for occupancy, 1 for render / collision state. 3. Count sorted semantic IDs, common local meanings use fewer bits than rare meanings. 4. Per pixel hit maps, screen pixels retain their world space hit addresses between frames. 5. Deferred semantic screen passes. Expensive behavior is grouped by layer after traversal. The result is not merely a voxel renderer. It is a semantic address space renderer. Core world model: the world is a disk resident matrix, XYZ, spatial coordinate. UVW, traversal /page /address coordinate. RGB, coordinate derived spectral identity. The simplest identity is R equals U equals X, G equals V equals Y, B equals W equals Z. In practice, this identity may be remapped through perceptual curves, local palettes, nonlinear warps, blue noise perturbation, or semantic overrides to avoid visible coordinate gradient artifacts. Minimal storage plan. At the base layer, each voxel address has 2 bits. Plain bit meaning plane 00 empty, plane 01 occupied, plane 10 render disabled / collision or metadata only, plane 11 render enabled. The 4 immediate states are: occupancy render flag ray behavior possible use 00 skip empty space 01 reserved streaming hint, debug, future use 10 skip for color, retain for systems collision, proxy, occlusion, XR comfort shell 11 stop ray visible surface hit. This is deliberately small. A renderer can test vast address ranges without fetching material tables, UV data, or full payloads. Bit and byte compactness. The proposal's storage advantage begins before compression. 2 1-bit planes cost 2 bits per address equals 0.25 bytes per voxel address. A 2 TB address store used only for the 2 base planes represents roughly 2 trillion bytes * 8 bits / 2 bits equals 8 trillion voxel addresses. That is approximately a 20,000 x 20,000 x 20,000 cubic grid before semantic compression, sparse paging, MIPS, payload tiering, or procedural reconstruction. The recommended compact page layout is: component typical bits notes occupancy 1 mandatory render / collision state 1 mandatory local semantic ID 0 to 8 only where needed. Count sorted page generation 4 to 12 cache validation, not per voxel when possible payload tier 0 to 3 often page level or run level. Component payload pointer typical bits notes 0 to 32 only rare visible / semantic cells. Most addresses should remain 2-bit cells. Semantic and payload data should be page local side channels, run length blocks, or extension pages, not universal per voxel baggage. The guiding rule: every voxel gets traversal bits, few voxels get semantic bits, visible semantic hits get payload access. This is how the architecture stays byte compact instead of becoming a disguised asset database. Pixel-centric raymarch explanation. Each output pixel asks one question: what is the nearest occupied renderable address along this camera ray? The ray starts at the virtual camera's position inside the hard disk-backed coordinate matrix. The camera is not outside an asset scene. It is inserted into the same XYZ/UVW/RGB address system as the world. For a pixel at screen coordinate, SX, Psi1. Construct camera ray from virtual camera pose. 2. Convert ray steps into XYZ/UVW matrix addresses. 3. Query resident occupancy pages. 4. If occupancy equals 0, continue marching. 5. If occupancy equals 1 and render flag equals 0, continue color march but record optional non-visual state. 6. If occupancy equals 1 and render flag equals 1, stop. 7. Write the hit address and attributes into the hit frame buffer. The pixel does not clear to nothing in the conceptual model. It searches until it resolves to either nearest visible occupied address or miss /background /fallback sky semantic. All render flags can begin disabled in storage or streaming state. A page only becomes visible when the traversal and residency systems decide it is valid for the current camera, LOD, and semantic budget. This makes the render flag a visibility and staging gate, not just a material toggle. Why disk is not directly raymarched. The SSD is the backing address space, not the real-time shader memory. The practical path is SSD world pages, OS/engine IO requests, RAM page cache, VRAM resident bricks, GPU raymarches resident bit planes, hit frame buffer, semantic screen shaders, final frame buffer. When a page is missing, the renderer should not stall the frame. It should use a fallback, missing page, coarse occupancy MIP, procedural color, previous frame reprojection, or sky/empty semantic. The SSD behaves like a spatial ROM. The GPU operates on a predicted resident working set. Per pixel hit frame buffer. The raymarch pass outputs a custom G buffer. Buffer suggested format purpose hit position RGBA16F or RGB32F and depth world XYZ and camera depth address R32UI/RG32UI UVW page, or compact address semantic R16UI or R32UI count sorted semantic ID state flags R8UI or R16UI occupied, renderable, hidden, dynamic, stale payload ID R32UI optional splat /procedural /neural payload pointer normal RG16F optional gradient or octahedral normal confidence R8UI temporal reuse quality. This hit map is preserved across frames. Frame n+1 reprojects frame n hit positions through the new camera, previous hit _XYZ, transform by current view / projection, predicted screen pixel, validate depth, semantic, page generation, and motion, reuse or refine. This is the architecture's strongest temporal advantage. The frame buffer is not just an image, it is a map from screen pixels to world addresses. Deferred semantic screen passes. The first pass should not execute arbitrary semantic programs. It should only traverse and record hits. Semantic complexity belongs in later screen space passes. Pass 1, occupancy raymarch, hit map pass 2, base coordinate color pass 3, semantic layer passes pass 4, splat / transparency / particles pass 5, lighting, reprojection, denoise, composite. Example layers. Layer reads writes base coordinate color hit _XYZ, semantic _ID RGB from coordinate manifold terrain hit _XYZ, normal, payload _ID refined albedo / normal foliage semantic _ID, seed, depth local splat clusters water depth, normal, motion reflection / refraction layer dynamic actors payload _ID, semantic _ID streamed detail and animation XR comfort hidden / collision flags depth only masks, comfort geometry. This keeps GPU execution coherent. Pixels with similar semantic IDs can be processed in tiles, masks, or compute dispatches instead of forcing the raymarch loop to branch into many unrelated handlers. Count sorted semantic bit depth. World semantics are not uniformly distributed. A typical region may contain a small number of very common meanings and a long tail of rare objects. Semantic frequency example encoding strategy empty /sky /background 50 to 80% implicit or 1 to 2 bits terrain /walls 5 to 20% 3 to 5 bits foliage /clutter 1 to 10% 5 to 8 bits. Semantic props / actors frequency example 1% encoding strategy local extension page unique events rare payload pointer. Instead of fixed width global IDs, RGBUVQXYZ should use local semantic vocabularies, region page, local semantic table, variable depth semantic code. This is spatial entropy coding. A forest page should not spend bits on city traffic semantics. A city block should not spend bits on coral reef semantics. Semantic payload tiers. The semantic ID should not always imply a large payload. Payloads should be tiered. Tier resident data use 0-1 occupancy and render bit only semantic ID and seed traversal, silhouettes, depth procedural class reconstruction 2-3 compact recipe full payload clustered splats, material refinement covariance, Gaussian detail, animation 4. The renderer should degrade gracefully. Offline / neural. Full payload missing, compact recipe missing, semantic seed missing, coordinate color missing, background / previous frame. Gaussian splat integration. Standard Gaussian splatting often begins with a large resident cloud, load splat cloud project visible splat sort blend. RGBUVQXYZ inverts this. Raymarch address space find first semantic hit activate only local splat payloads shade / composite. The voxel is not the final geometry. It is a semantic activation node. Example, semantic _ID equals oak _tree _large seed equals 88,123 payload _tier equals too far, 1 Gaussian billboard / color field mid. Clustered trunk plus canopy splats near, full branch / leaf splat set close, procedural bark and leaf microdetail. Reconstruction, compression, training, baking. The same semantic address can emit different detail based on distance, foveal priority, confidence, and payload residency. RE-written code policy. RE-generated code should not execute directly inside the frame loop. Recommended model, AI proposes semantic recipe validator bounds it compiler converts it to data, kernel ID, or Bitecode runtime executes only bounded kernels. Runtime representation, semantic_id kernel_id seed payload _id budget LOD policy. This makes AI useful as an offline semantic compiler while keeping the renderer deterministic, debuggable, and GPU-friendly. H100 vs RTX 5060 TOC, published anchors. The comparison is speculative for RGBUVQXYZ performance because no implementation exists yet. The hardware anchors are public specs from NVIDIA and board partners. Metric H100 SXM memory bandwidth 80 GB HBM3 about 3.35 TB/s. H100 PCIe/NVL class 80 to 94 GB HBM RTX 5060 T 16 GB OC 16 GB GDDR7 about 2.0-3.9 TB/s depending SKU about 448 GB/s at 28 Gbps, 128-bit FP32 class. AI/Tensor. About 67 flops. Data center tensor throughput. About 51-60 plus flops depending SKU about 23 to 25 flops estimated from 4608 cores and OC boost data center tensor throughput board power practical roll up to 700 WSXM offline research, giant caches, neural reconstruction. 300 to 350 WPCIe class server research. 759 AI TOPS class about 180 W consumer RTX prototype target. Sources: NVIDIA H100 product/spec pages, https://www.nvidia.com/data-center/H100/NVIDIA RTX 5060 family product page, https://GeForce/WWW.nvidia.com/en-us/geForce/graphics-cards/5060-series/RTX-5060 T16G gaming OC specs, https://www.mc.com/graphics-card/GeForce-RTX-5060-T-16G gaming-OC/specification. Speculative workload comparison. Relative to H100 SXM as 100 for this architecture. Workload H100 SXM raw bit plane traversal. Resident occupancy lookup. 100. 100. RTX 5060 TOC 35 to 50. 30 to 45. Reason consumer RTX has enough ALU but less bandwidth/cache RAM bandwidth and cache locality dominate count sorted semantic decode. Full random payload streaming. 100. 100. 60 to 80. 10 to 25. Mostly integer/bit logic, good fit for RTX HBM capacity and bandwidth dominate screen space semantic passes 145 to 70 coherent passes are RTX friendly. Workload H100 SXM RTX 5060 TOC reason temporal hit reuse 1007095 algorithmic reuse can narrow the gap Gaussian expansion 1002555 depends heavily on payload locality and splat budget neural fallback /training 105 to 20 H100 dominates training class work practical real-time desktop dev 35100 RTX card is the deployment reality. How RTX 5060 T can chase H100 class behavior. The goal should not be to make RTX 5060 T match H100 raw throughput. That is physically impossible. The goal is to make the workload so compact and coherent that the RTX card rarely needs H100 style bandwidth. Strategy. H100 Advantage RTX counter move huge HBM capacity keep only visible / predicted bricks resident massive bandwidth compress occupancy, semantics, payload tiers tensor throughput use AI offline, runtime uses compact kernels random payload tolerance reorder by screen tiles and semantic layers large scene residency page by camera velocity, fovea, and temporal hits brute force splat expansion activates splats only at visible semantic hits. The design target for RTX is less data touched more reuse more locality fewer payload fetches bounded expansion no arbitrary runtime semantic code. H100 equivalent performance definition. Near H100 performance on RTX should be defined narrowly. It cannot mean equal FP32, tensor, or memory bandwidth. It can mean similar visible result latency for a bounded scene class similar shaded pixel throughput after temporal reuse similar perceived frame stability under camera motion similar payload quality at the fovea. The target metric is not total world bytes processed. The target metric is bytes touched per accepted shaded pixel. If H100 shades a frame by brute force bandwidth and RTX shades a visually similar frame by touching 5-10x less data, the RTX implementation can approach the same user visible result for this renderer even while losing badly on raw hardware specs. Speculative equivalence levers. Lever H100 method RTX 5060T method occupancy keep larger page windows resident aggressive brick prediction and MIPS semantics tolerate wider IDs and tables count sorted local vocabularies payloads fetch more full payloads TID fallback and foveal priority. Lever. Splat detail. H100 method. Expand more candidates. RTX 5060T method. Visible hit-only emission. Stability bandwidth absorbs misses previous frame hit _XYZ reprojection. AI detail runtime neural capacity offline baked recipes and compact kernels. The research win is not pretending the RTX card is an H100. The win is showing that the RGBUVQXYZ data model changes the problem enough that an RTX card can produce H100-like visible behavior for sparse semantic worlds. Proposed RTX 5060T frame budget. At 1920x1080, one full resolution pass has about 2.07 million pixels. In stereo VR, this effectively doubles before foveation or reprojection. Speculative first prototype targets. Stage 1080p mono budget RTX strategy. Ray setup. Occupancy March. 0.2-0.5 ms. 2 to 5 ms. Compute shader, tiled dispatch. Resident bricks, empty space skip, MIPS. Hit buffer right. Semantic layers. 0.5-1 ms. 1 to 4 ms. Compact formats. Masks, tiles, deferred passes. Splat expansion. Temporal reprojection. 1 to 6 ms. 0.5-2 ms. Strict per semantic budget. Reuse stable hit _XYZ. Composite. Initial target. 1080p mono, 30 to 60 fps. 0.5-1.5 ms. 1440p mono, 30 fps with reprojection VR, foveated and temporal required. Conventional screen pass. The H100 can validate large worlds and neural forward/payload strategies, but the RTX card should define the survival budget. Pipeline diagram. Hard disk /SSD-XYZ UVW RGB matrix V page index and local semantic tables VRAM streaming cache VRAM resident bricks V GPU raymarch pass, empty. Continue, occupied and render off. Continue color, keep hidden state, occupied and render on. Stop at nearest hit V per pixel hit frame buffer, hit_XYZ, hit_of, semantic_ID, depth, state flags, payload_IDV deferred semantic screen shaders. Base coordinate color, terrain, foliage, splats, water, XR masks V temporal reprojection and composite V display frame buffer. Critical risks. Risk why it matters. SSD random reads. Color space aliasing. Camera motion can scatter page requests. XYZ equals RGB can create artificial gradients. Mitigation. Predict by camera velocity, keep coarse MIPS, never block frame. Nonlinear color manifolds, palettes, semantic overrides. Payload explosion. Branch divergence. Splats //covariance can dominate bandwidth-tid payloads, per layer budgets, fallback recipes. Per hit semantic execution can trash GPU coherence. Transparency. Dynamic edits. Splats and volumetrics need order /compositing. Deferred semantic screen passes. Limit transparent layers, depth buckets, stochastic transparency. Changing disk pages can invalidate caches. Tooling complexity semantic compression can become opaque. Internal critique, draft weaknesses. Page generation IDs and dirty region updates. Debug views for occupancy, render flags, semantic IDs, residency. The naive version of this proposal was too excited about position equals color and not strict enough about residency. Directly raymarching a 2 TB SSD address space from the GPU is not viable. The corrected version treats the SSD as a backing store and makes VRAM resident bricks the real-time target. The first version also risked turning semantic IDs into arbitrary scripts. That would be powerful but would destroy determinism and GPU scheduling. The revised version moves semantic work into bounded screen space passes and treats AI as an offline compiler. The proposal also needed a clearer RTX story. H100 cannot be the design center because it hides the exact bandwidth limits that make the architecture interesting. The RTX 5060 TOC should be the discipline card. If the format survives there, it becomes credible. Improved research thesis. RGBUVQXYZ should be evaluated as a disk-resident semantic address space renderer that transforms screen pixels into stable world address hits, then performs bounded deferred semantic expansion. The measurable research question is: can temporal hit reuse, semantic entropy coding, and payload-tid screen passes make a 16 GB consumer RTX GPU behave like a much larger memory system for sparse procedural worlds? That is a strong NVIDIA-facing question because it touches RTX, direct stretch-style streaming, neural asset compression, shader execution reordering, foveated rendering, and Gaussian splat acceleration without requiring the claim that it replaces conventional rasterization. Prototype milestones 1. Build a CPU-generated synthetic XYZ/UVW/RGB bitplane volume. 2. Stream fixed-size bricks into VRAM. 3. Implement GPU raymarch pass writing hit_XYZ, depth, flags, and semantic_ID. 4. Add temporal reprojection from previous hit_XYZ. 5. Add count sorted local semantic tables. 6. Add deferred semantic screen shader layers. 7. Add payload tiering and local Gaussian emission. 8. Benchmark RTX 5060 TOC against an H100 reference run. 9. Add VR/foveated mode. 10. Publish debug views and reproducible scene traces. Benchmark metrics: minimum useful metrics, metric raise per second, average voxel steps per pixel. Y base traversal throughput scene / raymarch difficulty bytes fetched per visible pixel hit reuse percentage core efficiency metric temporal stability payload misses per frame semantic layer cost streaming pressure deferred shading overhead splat emissions per hit page faults per camera degree expansion control XR motion stress frame time 50p / 95p / 99p. Best headline metric, visible bytes per shaded pixel. Spike behavior. If that number stays low on RTX hardware, the architecture is doing something genuinely useful. Final position above XIS is strongest when it avoids trying to be a universal replacement for raster graphics. Its strongest identity is semantic address space rendering for huge streamed worlds. The architecture is credible if it keeps 4 promises. 1. Raymarching stays simple. 2. Semantics stay compact. 3. Payloads are visible hit activated. 4. Temporal hit maps reduce rediscovery. The most exciting form is not a voxel contains geometry. It is a visible address invokes meaning, and meaning expands only as far as the frame budget allows. That is the idea worth pitching.